Hi, I'm Zor. Welcome to Zor Education. I would like to start a new topic. It's about systems of trigonometric equations. Well, first of all, about the concept. What is the systems? What are the systems of trigonometric equations? Well, you know that trigonometric equation is equation which has some trigonometric functions involved, right? So systems of trigonometric equations are exactly similar. It's some systems of equations with more than one unknown, and certain trigonometric functions are involved in this system. Now, is there any general methodology of solving the systems of trigonometric equations? Well, no, but regularly, the substitution method, which is similar to substitution method in other systems, in algebraic systems, is usually something which might be involved, not necessarily. Actually, the more interesting examples of systems of trigonometric equations do contain the substitution as part of it, but that's the most trivial part. The most interesting part starts after the substitution is done, and you have to basically solve certain trigonometric equations. So the best way to learn about systems of trigonometric equations is to solve them. And you know my recipe for all kinds of learning math. It's just solve problems. The more you do, the more difficult the problems are, the more your mind is prepared for an unknown, whatever you can meet in your real practical life. And that's the only recipe which I have in this particular case. So no particular skills will be developed by solving trigonometric equations or systems of trigonometric equations. It's just development of your mind, your creativity, your critical abilities, your analytical abilities, your ingenuity and intelligence. All right, so I would like to present one particular system, and I will just solve it. And then there will be certain problems which I will just continue analyzing and explaining, etc. So this particular lecture will be about one particular problem, one particular system of trigonometric equations, and let's just follow the logic of this. The system is as follows: a sine x plus b cosine y equals c, and x plus y equals d. So, two trigonometric equations with two variables, x and y, and as you see, there are some trigonometric functions involved, which allows us to basically say that, okay, this is a system of trigonometric equations. Although only one of them is really trigonometric and another is more of traditional algebraic form. Now, this is one of the simplest examples, and it's basically solved using the regular substitution method, which you might imagine would do in this particular case. So what do? We resolve the second equation for y in terms of x, which is this, and substitute into the top equation to get one trigonometric equation with one unknown, x. After we define x, then we can just define y as well. So, what kind of trigonometric equation will be as a result? A sine of x plus b cosine of d minus x equals c. Now, obviously, I cannot solve it without certain manipulations, and the first manipulation, which basically is natural, is to open up cosine of the difference between two angles. So it will be a sine x plus b cosine d cosine x plus b sine d sine x equals c. Alright? Cosine of the difference is cosine cosine plus sine sine, and the coefficient b goes to both sides. Now, if you remember in one of the lectures which was dedicated to trigonometric equations, I was solving equation of like p sine x plus q cosine x equals whatever a, I don't know. And the way how I solved this equation was I multiply and divide this by r equals to square root of p square plus q square. So I have r p over r sine x plus q over r cosine x equals a. And then I basically interpreted p over r as sine of some angle and q over r as a cosine of the same angle, and using this it was possible. So let me remind you the whole technique actually in details, and then I will apply it to this guy. But first we have to convert it into this form. So we bring together everything about sine x and about cosine x, right? So it's b cosine d cosine x plus a plus b sine d sine x equals c. So basically, I will call this p and this q. These are constants, right? Because d is a constant, and a is a constant, and b is a constant. So they are known constants. So instead of going into large formulas, I'll just use the letters p and q. P signifies b cosine d, and q signifies a plus b sine d. So what I have is p cosine x plus q sine x equals c. How to solve this equation? As I was saying before, I will have r equals to square root of p squared plus q squared. So if I'm talking about solving this equation, I presume that they are not at the same time equal to 0, because otherwise it's not an equation. So that's why r is not equal to 0, obviously. Now, p over r can be a cosine of some angle phi, and q over r can be a sine of this angle phi. How can I find this angle phi? Well, let's think about this way. If both p and q are positive, now r is always positive, so cosine and sine are positive. Now cosine, as you remember, is abscissa of this point. This is cosine, and this is an ordinate is a sine. If this is a unit circle, and this is an angle phi. All right? So if p and q are positive, then I can actually say that the phi can be arc cosine of p over r. Actually, you know what? Let me just invent one particular angle, alpha, which is arcsine of absolute value of P over R. So absolute value is always positive. Okay? Absolute value is always positive. So I always have this angle alpha. So it's not phi, it's alpha. Now, angle phi is defined by these identities. So now we have different cases. If P greater or equal to 0 and Q greater or equal to 0, then my angle phi is equal exactly alpha, because it's in the first quarter. Now, if P, which is abscissa, is greater or equal to 0, but Q is less than 0, so it's here. So abscissa P is greater than 0 and ordinate is less than 0. Then phi is equal to minus alpha. Right? This is alpha. This is alpha, this is minus alpha. Now, if P is less than 0 and Q is greater than or equal to 0, P is here, so it's here. So angle phi is equal to pi minus alpha. And finally, if both of them are negative, then phi is equal to, it's here, pi plus alpha, right? So if alpha is defined as this, where absolute value of P is always positive, that's why alpha is here, then whatever my P and Q are, I can always find angle phi using the angle alpha and pi in this particular case, depending on P and Q, and definitely sine and cosine of phi would be whatever I'm looking for. Now, having that angle phi, which is calculated as through alpha and these inequalities, I can say that here, instead of this particular equation, I can put R cosine phi cosine x plus sine phi sine x equals C. Because P over R is cosine phi and Q over R is sine phi, right? So R is a factor multiplier factored out. From which we can always see that cosine of x minus phi, because that's exactly what's in these parentheses, is equal to C over R. Which brings us to solution. X is equal to phi plus minus arc cosine of C over R plus 2 pi n. Right? So x minus phi is equal to arc cosine plus minus arc cosine of C over R and plus p n, 2p. And then phi should be added. Basically, that's the solution. That's x, and then the d minus x would be y, obviously. So y is equal to d minus phi, and since it's plus or minus, doesn't really matter in what order I put it. And n is any integer, so again, it doesn't really matter whether it's plus or minus. So any pair of x and y, which is calculated, actually, you know what, I don't even have to use the same letter n. I can use letter anything else, because it's still a period anyway, right? All right. Oh, no. N is important here. And in this case, I should really put minus, because it's minus. So x plus y would always be d. I really have to preserve the sign, so it's not plus minus, it's minus plus, right? Because it's d minus x, so I have to reverse all the signs. Minus phi, instead of plus minus, I should put minus plus, and instead of this plus minus, where n is any integer number, obviously. Okay, now x plus y would be equal to d, but as far as this relationship, it doesn't really matter about 2 pi n because it's a periodic function. All right, so that's the solution. What's interesting is it's a relatively simple system because all I did was I substituted the unknown to the first equation, reducing the system of two equations with two unknown to one equation with one unknown, and that latter was actually kind of the thing which we used to solve before. It's this type, cosine and sine with some coefficients. I will probably introduce to you some more special techniques whenever we will go through problems related to systems of equations. And again, the more problems we solve, the more these special techniques you will absorb, and that's not, you know, it's just the tools. You don't have to really like remember it by heart or anything like that. But if you try to do it yourself first before listening to my explanations, it will definitely enrich your repertoire of your techniques which you can use. So I definitely suggest you to go again maybe through this example as well, just by yourself. And then for whatever problems will be introduced in this topic, try to solve it themselves and then listen to the lectures. Well, that's it for today. Don't forget that unizor.com contains not only these lectures or problems, etc., but an entire process, educational process, which you can actually incorporate into your studying, because you can enroll, or your supervisor can enroll you, your parent can enroll you in any topic. There are or there will be exams for each topic. Some of them are not yet ready, but most of them actually are ready right now. So the exam will give you a very good picture of how well you master the particular topic, particular part of this course of mathematics. Well, that's it. Thank you very much, and good luck. Hi, I'm Zor. Welcome to Unizor Education. I would like to present you a couple of problems related to systems of trigonometric equations. As usually, my recommendation is try to solve these problems yourself first before you listen to this lecture. Now, as you know, I'm trying to position this course as the one which develops your mind, your creativity, your analytical abilities, etc. And it's the process of thinking about something that's what actually develops your mind, in as much as exercise in a gym develops your muscles. So try to think. I mean, that's the only recommendation which I have. If you listen to the lecture without previous thinking about the problem, that's just not even 10% of the work which you would like actually to get for your mind, for your abilities. So it's very important. Think about these problems first. Doesn't really matter whether you solve them or not yourself. It's important to spend time and think about how to solve them. And by the way, there are certain problems which I present in this course as examination problems, and I don't provide these lectures with answers. These are just multiple choice answers which you have to choose, and just plain guessing will never give you the perfect score. And it's a perfect score on the exam, which means all problems must be solved correctly. That's what your goal is. Okay. Without further ado, I have two problems. One is, well, actually both seem to be easy. However, in both there is certain trick or carefulness, if you wish, which you would like to exercise. Okay, one looks very simple. Sine x sine y equals a, cosine x cosine y equals b. So that's the system. Two variables, x and y, and two equations. This is the system. Now, I don't know about you, but looking at this, I immediately see the formula for cosine of a sum of two angles and cosine of a difference of two angles. So cosine of x plus y equals cosine x cosine y minus sine x sine y, and cosine of x minus y equals cosine x cosine y plus sine x sine y. Now, what does it mean in our case? Well, I have the product of the cosines and I have a product of the sines, which means immediately I can conclude that cosine of x plus y is equal to product of cosines minus product of sines, which is b minus a, and cosine of x minus y equals a plus b. Transformation from here to here is invariant, which means it doesn't add additional solutions and doesn't lose any solutions, because this is invariant transformation. Okay, so I have this system. Now, is it easier? Of course it is easier, because it actually falls into something like cosine phi is equal to whatever, p for instance, and we know the solution to this, and it's already actually addressed in the previous lectures, is that the angle phi is equal to plus minus arc cosine of p plus 2 pi n, where n is any integer. So from here, using this, we can derive the following. X plus y equals plus minus arc cosine of b minus a plus 2 pi n, and x minus y is equal to plus minus arc cosine a plus b plus 2 pi m. I use a different integer because it's completely different things, and we might actually use different integer, not necessarily the same. So in this case I can add, for instance, 0, and in this case 1, and it will be a solution. Or in this case minus 3, and in this case plus 5. That's a solution. Alright, so that's what I have. Well, now this seems to be like a system of two linear equations with two variables, which is very simple to solve. However, let's be very careful about plus or minus in this case, and m and n in this case. I would like to address them, how should I say it, very carefully. Let me do it this way. Since x plus y can be anything from this, let me just represent it in two cases separately. Arc cosine b minus a plus 2 pi n, or it can be minus arc cosine of b minus a plus 2 pi n. and x minus y can be plus arc cosine of a plus b plus 2 pi m, or it can be minus arc cosine of a plus b plus 2 pi m. Now, these two cases, in these two cases, they actually should be combined into system. So, can I have plus here and minus here? Yes. Minus here and plus here? Yes. Plus and plus? Yes. Minus and minus? Yes. So it's 4 different systems I have. And 4 different solutions, and each solution is not actually a single solution because there is this integer n or m which should be added. So let me just, as one particular example, like one case, the case number 1, I'll consider first, which is x plus y is equal to this and x minus y is equal to this, from which I can conclude by adding these two, y and y will be reduced, will be 2x here, so x is equal to 1/2 of arc cosine b minus a plus arc cosine of a plus b, plus, well, pi times m plus n. And y is equal to 1/2. I have to subtract from this, I subtract this, so x and x will be reduced and will be 2y. So that's why 1/2 here. So it would be arc cosine b minus a minus arc cosine of a plus b. And from this I will subtract, and that will be n minus n. So b and a are constant, so there is no problem with this. Now, this is many pairs of solutions where m and n are any integer numbers. Now, it actually natural to think that, hey, if m and n are any integer numbers, can I just replace m plus n as k and say, and m and n minus m as l, and say that k and l are anything, any integer numbers? Well, not exactly. Because look at these. You see, x plus y should give me something which is multiple by 2 pi. And these two always give me something which is multiple by 2 pi. For instance, if I add them together, I will have 2n. If I subtract them, it would be 2n, right? So k and l also must be of that particular property. If I sum them together, they must be even. So I will have 2 pi here. Because if I will have, for instance, 0 and 1, so I will have 0 here and pi here, and my sum would be sum of these. My sum would be like arc cosine of this, because arc cosine of a plus b will be reduced, will be plus 2 plus pi, just plus pi, right? Because k is equal to 0, l is equal to 1, it will be plus pi. And that is not right, because the period of the cosine is 2 pi, not pi. So if my cosine of x plus y is equal to b minus a, I cannot have pi multiplied by something, or like 1, for instance. I have to have 2 pi by something. So k and l can be replaced, m plus n and n minus l, with integers k and l. However, there is one particular requirement. Their sum and their difference must be even, which means either they're both even or they're both odd. So any way you would like to express this, either with m and n, saying m and n are any integer numbers, or you can say pi k and pi l, but then the condition is that both k and l should be either both odd or both even. So their sum and their difference is always even. Okay, so that's the little twist which you have to really think about it. Now, now I can exactly in the same fashion I can have the second choice. If I will have, let's say, plus here and minus here, and you will see exactly the same type of manipulations. Well, let me just do it, just one. So it's this and this, right? So their sum would have a minus. So x is equal to 1/2 arc cosine b minus a minus arc cosine a plus b plus pi m minus m, actually m plus m, because I'm summarizing. Yes, I'm summarizing. And so let me wipe this out so it doesn't confuse. And y is equal to, if I subtract, it would be sum. So 1/2 arc cosine b minus a plus arc cosine of a plus b plus p plus pi n minus m. So basically, I exchange the x and y. And looking at the original system, you remember, right? Sine x sine y is equal to a, cosine x cosine y is equal to b. Obviously, if I change x and y values, it will be exactly the same thing because it's symmetrical relative to x and y. So I should expect actually that if pair x, y is a solution, then the opposite, y takes the value of x and x takes the value of y, is also a solution. And then other two solutions, when I have minus here and plus here, similarly, it would be minus here and either plus here or minus here. Doesn't really matter. So these four different formulas, 1, 2, and then 3 and 4 would be with minus here. They represent four different sets of solutions, and sets because m and n can be any integer numbers, which would actually go through all that. These four formulas, each of them represents a set of solutions, represent a complete set of solutions to this particular system of equations. All right? Well, that's it. Now, in the beginning, it was simple. I just recognized the cosine and the cosine of sum and cosine of difference. But then, at the very end, you really have to be very careful with these cases. That's what probably very important. So sometimes there is an easy solution, but you really have to watch every step so you don't lose anything or you don't add anything, etc. And the next problem would be even more educational in this particular way. Okay, this is a system of three equations with three unknown variables. Okay. Now, what actually I was thinking about examining this particular system is, hey, it would be nice if I can express tangent of sum of three angles in terms of tangents of each angle. Then I will have only tangents, which means I can replace tangent of x with some variable, tangent of y with some variable, and tangent of z with some variable, and have another system of three equations with three variables, but it's not trigonometric equations anymore. So these will be just a regular algebraic system of three equations with three variables. But obviously I don't remember, I don't know the formula, tangent of three, sum of three angles. I do remember for two, and I do remember that tangent of sum of two angles is expressed in the tangent, in the terms of tangent of each one, right? So you remember this. So tangent of phi plus psi is equal to tangent of phi plus tangent of psi divided by 1 minus tangent phi tangent psi, right? This is the formula. And again, I do remember the formula of sum of two angles. I do remember actually sine, cosine, tangent. Cotangent I don't, but it's very easy to derive. Same thing with secant and cosecant. But I do remember sine, cosine, and tangent of sum of two angles. These formulas I do remember. So this is one of them. So if the sum of two angles can be, tangent of sum of two angles can be expressed in terms of tangent of each one of them, then obviously I hope that the tangent of three angles summed together also is expressed. But let me derive this formula, and obviously that's just step by step, first two and then the third one. So tangent of x plus y plus z equals. So x plus y is one variable, right? One angle. Tangent of x plus y. And tangent z is another. 1 minus tangent x plus y tangent z equals. Okay. Now let's express tangent of x plus y in terms of tangent x and tangent of y. So I will have tangent x plus tangent y over 1 minus their product. Plus tangent z divided by 1 minus, same thing here, tangent of x plus tangent of y over 1 minus tangent of x, tangent of y times tangent of z, right? So what I will do is, in the numerator, I will multiply this by this, and it will be one longer numerator. In the numerator, I will have a fraction where numerator will be this plus this plus this, multiply. Now, and the denominator in the big numerator will be 1 minus product of tangents. Same thing here. Also, I will have in the big denominator, I have, if I will multiply this by this, and this by this, I will have numerator whatever I will have, and denominator 1 minus product of tangents. And I will just drop both denominators, right? I will use only numerator from here and numerator from there, because denominators will be the same. So what will be the numerator in the top one? So it's tangent x plus tangent y plus this 1 minus tangent by tangent multiplied by this. So it would be 1 by tangent, so it's plus tangent z, and it will be minus their product. Tangent x, tangent y, tangent z. That's my numerator. Now, what will be in the denominator? So the numerator part of this thing, it's 1 minus this, 1 minus tangent by tangent times 1, right? So it's 1 minus tangent x, tangent y, minus this times this, which is tangent x, tangent y, z, and minus again tangent y, tangent z. So that's my answer. Now, as you see, this is symmetrical relative to x, y, and z, right? We can transform them in any way we want, and this is also symmetrical: x, y, z, and this is x, y, x, z, and y, z. So looks like we have the right formula. Now, using this, let me just take the tangent of the last equation, and I will have tangent of x plus y plus z, and I can express it in this way. I will have minus 3 on the right, because tangent of arctangent is obviously whatever the argument is from definition of the arctangent. And then I will have the 3 equations where only tangents of x, y, and z are present, right? So I can actually replace tangent x with a variable u, tangent y with a variable v, tangent z with a variable w, and I will have an algebraic system of equations relative to u, v, and w, because only tangents are present. However, and here is a very important twist which you really should not lose your focus from. Yes, x plus y plus z equals something. That's fine. But then I take the tangent of both sides. Is this an invariant transformation? So let me ask again. If p is equal to q, is tangent of p equivalent to tangent of q? Are these two invariant? Are these solutions exactly the same as these, and these exactly the same as those? No. Why? Because the tangent is a periodic function, and as we know, we can add to this angle q, for instance. Pi k, and it will be exactly the same equality. So not only p is equal to q is the solution of this, but also p is equal to q plus pk, pi k, right? Where k is any integer. So this thing has infinite number of solutions, right? So if p is a variable and q is a constant, let's say this is 3. Then from this we derive p is equal to 3 plus pi k, not just p equals to 3. So it's not invariant, which means that we have to be very careful at the very end when we will derive some kind of solutions to our system after we have taken tangent of both sides. We have to be very careful examining our solutions, because we might introduce certain solutions which actually do not belong. Right? So, keeping this in mind, I would still like to proceed with taking the tangent of both sides and replacing my variables with these new variable substitutions. So I will have u times w equals to 1, v times w equals to 1, right? Tangent of y is my new variable v, tangent of z is still w. And on the left I have this thing, and it's equal to minus 3, right? Because I took tangent of both sides. So let me just put it, which is u plus v plus w minus uv w divided by 1 minus uv minus uz w minus vw equals to minus 3. This is the system which we can attempt to solve, but this is algebraic, it's not trigonomic, which I hope makes it simpler. Now let's see if we can solve it. Because if we can, then from u, v, and w we'll just know how to derive x, y, and z from each of these guys, right? Okay, so what's my um, proposed plan to solve this particular system of equation? Well, let's, considering u and v are kind of symmetrical in this particular case, in the entire system, right? I would attempt to use w as a base variable, and I will express u in terms of w, v in terms of w, and substitute everything in the third, and then I will get only one equation with one w. Now, obviously, I have to think about what if my denominator equals to 0. It means no solution. So I have to really be careful about this as well. So there are a lot of things to be careful about this, right? So the last equation I actually can rewrite as this numerator is equal to minus 3 times denominator, right? So I can just multiply both sides by denominator to have a linear without any kind of fraction. So from this, I will have u is equal to 1 over w, v is equal to 1 over w. Again, I'm doing it kind of freely, but I have to really think about what if w is equal to 0, right? Is this a solution? Well, each one of these cases must be examined separately. What if w equals to 0? What if 1 minus uv minus uw minus vw equals to 0? So these are separate cases which I have to examine separately. Don't forget it. Even if I forget it when I'm presenting this lecture, you should not. All right, so having these, I will substitute it into this equation, and what will I have? Well, let me just write u is 1 over w, plus v is 1 over w, plus w, minus u times v, it's 1 over w squared, and w, so it will be 1 over w. Now, equals to minus 3 times denominator, which is 1 minus. Now, uv is 1 over w squared, right? Minus uw, which is 1, right? And vw, which is 1 as well. So that's my equation. Now, let me just do some reduction here. This and this, right? Now, let me rewrite it. So on the left I have 1 over w plus w. On the right I have this minus and this minus and this minus, so it's basically 3 over w squared plus 3, right? Minus minus, so it's 3 over w squared, and minus minus plus 3. And now I will multiply it by w squared, and I will get w plus w cubed equals 3 plus w squared. I multiply everything by w. And I already kind of consider that this case should be separately. And let me rewrite it like real equation. W cubed minus no, I think I made a mistake. It's 3w. Yes, it was 3w, so it's 3w. Sorry. Minus double 3w squared minus plus w minus 3. Right? Right, equals to 0. So w minus 3. W cubed minus 3w. Right. Okay. Now, I have to solve this equation of the third degree. Right? So it's not such an easy thing. However, in this particular case, I immediately see a very important thing. If I will factor out w squared from the first two, I will get w minus 3, and this is w minus 3. So it's equal to w squared plus 1 times w minus 3 equals to 0, which means that either this is equal to 0 or this is equal to 0. Now, this is not equal to 0 because it's square plus 1, right? Square is always non-negative, plus 1 is always positive. So w is equal to 3 is my solution. And obviously from here, my u is equal to 1/3 and my v is equal to 1/3. These are all solutions. Well, am I almost done? Well, look, I mean, if tangent of x is equal to 1/3, then x is equal to arc tangent of 1/3 plus pi k. Y is equal to arc tangent of v, which is 1/3 as well, plus pi m, and z is equal to arc tangent of 3 plus pi n. Is that it? Well, unfortunately no. Well, first of all, I did not check all these cases, remember? If w is equal to 0, well, w is not equal to 0, it's 3. How about 1 minus u, v minus u, w minus v, w? Is that equal to 0? I hope not. So this is 1/3 and 1/3, 1/3, 3, and 1/3, 3 equals to, this is 1 minus 1 of this one, so it's minus 1 and 1/9, something like this. Okay, so that's good. Well, at least I did not, by multiplying by this, I did not introduce new solutions, which is good. So far so good. However, there is one detail which I did mention before, and it should actually play the very important role right now. Remember this? When I took the tangent of both sides, I was talking about this as a non-invariant transformation. So, if k, m, and n are any integer numbers, obviously not all the numbers fit this particular equation, because arc tangent of minus 3 is always between minus pi over 2 and pi over 2, without including the boundaries, right? So whenever we sum these together, k plus m plus n must be in such particular value that altogether it falls into this particular interval. Is it possible? Well, let's just think about it this way. Let me just make some kind of evaluation of the values. What is arc tangent of 1/3? Well, remember the function tangent looks like this, right? This is minus p over 2, this is pi over 2, this is 0, y, x. Now, tangent of pi over 4, which is 45 degrees, tangent is sine over cosine, it's equal to 1, right? So this is 1, and this is pi over 4, right? Well, it's not exactly half of this distance. Let's make it a little bit better. This is pi over 4, and this is 1, all right? Now, so as the tangent, as the angle increases, the tangent increases. The angle decreases, the tangent decreases to 0. So I need 1/3. So from 1, I should go to somewhere here. So it's less than p over 4, less than 45 degrees. By how much less, I don't know. But, well, considering the tangent is, diminishing in some way, well, maybe it's 20 degrees, maybe it's 10 degrees, something like this. Let's just assume, for argument's sake, that this is around 20 degrees, right? So this is around 20 degrees plus pi k. Y is also about this. And z is... Now, 3 is somewhere here, right? If this is 1, this is 3. So it's greater than p over 4. And again, this is 45, this is 90. I don't know how it is. Maybe 80, approximately, right? I mean, it doesn't really matter whether I'm exactly evaluating the value or really approximately. Can I choose k, m, and n in such a way that the sum of these would be arctangent of -3. Now, what's arctangent of -3? That's somewhere here, right? So let's say it's -80 degree, something like this. Well, probably yes. I can put something like, I don't know, -3 here, or -2, for instance, here, and 1 and 1 here, and I will be somewhere close. So I think I can play with these numbers in such a way that their sum would be within this particular interval. Again, being a little bit more precise with my evaluation, maybe I will have a calculator or something like this, I will definitely be able to find integer k, m, and n, which would satisfy this particular equation. And it's not just one triplet of k, m, and n, because I can increase one of them and decrease another, and that would be exactly the same thing. So basically what I'm saying is that there are a lot of solutions. They are expressed in this general formula with a condition that k, m, and n should be such that the sum of these three angles is within this particular interval somewhere. Well, basically that concludes the full solution of this particular equation. So, what's important? I think it's very important to understand that taking the tangent of this particular equation is not an invariant transformation. Now, everything else, whatever we did, was, well, really some kind of technicality, I would say. Taking, for instance, deriving the formula for a tangent of three different angles summed together, that was, trivial, basically. I didn't know the formula, I just derived it on the fly. And then, when I had this converted into algebraic system of equations, it was a little bit maybe unusual to have the system which resulted in the equation of the third degree. But it was such an equation of the third degree where you very easily see the solution. So basically that was not something unusual. But I think the first one, that the tangent of both sides is not an invariant transformation, is very important for you to think about. What I would suggest right now is take these two problems and try to solve them yourselves. And again, think about what kind of solution you get, what kind of integer k, m, n, whatever, in both cases, for both problems which I have presented, what kind of values are allowed, what's important. Well, basically that's it. Thank you very much, and I will try to put maybe some more problems with some interesting twists if I can. Thanks again, and good luck. Good luck to you.